introduce my friend, Joellen Russell. My honor, absolute honor to have her visiting here and introduce her. So Joellen got her bachelor's degree in Harvard in environmental geoscience. So let's just say follow her there, all right? PhD at Scripps Institution of Oceanography with Andrew Dixon. Okay, so check mark oceans. Postdoc at UW and as a Giselle fellow. So check mark atmospheres there. And then she went to Princeton and with the GFPL group, then worked to bring all of this knowledge together as a model. And dynamicist maybe?
Because the planet is cool.
And
Anyone in the right audience?
all along the way, bringing this enthusiasm, I'm sure. So right now, full professor at University of Arizona in beautiful Tucson, where I was just a couple of weeks ago, and apparently it's cold and rainy in Arizona all the time. That's my visit there. Okay, some honors, there are many. I'm just going to list some of the top ones. So Joellen is the Thomas R. Brown Distinguished Chair of Integrative Science. You are a full professor, you're a professor in multiple departments. Is that, I didn't have a chance to ask you that, but it's departments of geosciences.
Hydrology and atmospheric sciences, planetary sciences, and applied maths.
And I know.
It's only so that I can steal all the awesome grad students. But you do actually have to interview and they have to vote and check your CV and,
Well, good job. Okay. I think that's honorable too. Incredible, really. University distinguished professor and just last on my list, but not last on the list is a Fulbright U.S. scholar. This is just in the past couple of years. Very excited to see this talk and let's go, Joel.
Thank you. I appreciate it. It is a delight to be here. UC Irvine has been one of we watch here because we're more of a traditional geology department and you guys have got the system science thing totally going and it's just wonderful. I check in the web page, all the people I need to see, I'm not going to be here long enough. But to all your students, you are super lucky. This is the right spot to be in at the right time. So let's see. I think I just put this. It's on here. There's a reason that the clicker's not working now.
It's doing this the other day. No. Yeah.
It was working 5 minutes ago.
There's a couple.
Phones or wrong clicker.
I think that one's dead.
Okay, I can do it. I don't know. I don't need a clicker.
Oh,
You know what? I can just do it from my laptop.
okay.
Oh, you guys have a nice round room. Oh, is it going? Oh,
Okay,
excellent.
just click the
I
side.
always start with the pale blue dot, and the reason is because I totally think Carl Sagan is awesome. And he's the one who told NASA to turn the Voyager probe around as it was leaving our solar system and look back at our tiny little blue planet. And we've now found, he didn't, but he didn't even live to see the Kepler mission, right? Where we found thousands of planets orbiting other suns. So awesome. And so I like to start there because it's the only blue one we've ever found, right? We're still looking. We're sure there will be, but we've never found one. We've never seen one. Everybody's like, oh, there's water on Mars. I'm like, you mean there's like some ice under some dirt? I mean, oceans, right? It means that our climate is very special. And it has this enormous role that it's playing today and will be playing tomorrow and for the next 200 years. In fact, it's so important that the Weather Service, the National Weather Service, 5 years ago, there was a bake-off between the traditional atmosphere-only weather model and a coupled climate model from GFDL. And the coupled climate model won. Now, this is not a surprise to those of us who do a little oceanography. We're like, yeah, ocean's getting hot. You need to know where all that heat is. And my dad says, and it's terrible, joke for an old guy, says, you know, the ocean's like a box of chocolates. You blow the surface layer off, you never know what you're gonna get. Might be a really hot deep layer, might be cold water, and it matters, right? Cold water will make you, you know, that hurricane might get stopped dead in its tracks. Right, cold water, or you could be Harvey and you can take off the top layer and the next layer and the next layer and the next layer and just be hot all the way down, right? Dumping rain on Houston. So we know that it really matters. And of course, so we've had this convergence of climate weather modeling. And I remember listening very carefully with I won't tell you which certain dynamics that said, ooh, pretty soon, you know, the weather models will be so good, you'll be using them for climate. I'm like, or the weather models will be so awesome, we'll be using them for weather, and guess who wins? That'd be oceanographer, thank you. It matters. It matters a lot. And part of what I want to see is a transition to not just real-time weather, but how about real-time carbon fluxes? How about we actually look at the winds, and where it's blue, it's going into the ocean, and where it's red, it's coming out of the ocean. I love this. This is our dynamic ocean. And it's really tough to communicate this to regular people, because if I just showed you a picture of the beautiful ocean, you'd be like, yeah, that's blue and it's a horizon. Okay, boring. But in fact, we know that there are really big changes going on. Now, I always love starting here because everybody, you know, my crazy uncle always says, it's the volcanoes. And of course, I always say, well, look, if you can point out Pinatubo, Agog, and El Chichon on this map, I will absolutely agree with you. What? No, you can't? No. But the greenhouse gas index is scary. This is from NOAA, and it's basically the radiated forcing watts per square meter for CO2, methane, carbon, and nitrous oxide, CFCs, etc. Now, I know we have some methane people here, and I apologize for showing this graph because it says there's no big change in the forcing for methane. It does. What does it say there is a big change in? CO2. We're in trouble. We're in big trouble. This is forcing. Okay. All right. Here's a double whammy with we're in trouble. And yes, I did start with oceans, and then I went to carbon. Guess where I'm headed? Ha ha ha. Okay. So pandemic hits, right? Now, do you see a big difference in the seasonal cycle after the lockdown as opposed to before the lockdown? No. How scary is that, people? The whole world shut down. We all stayed home, and it didn't do squat. Well, actually it did. You know, we cut our emissions by more than 7% worldwide. We did. It was a huge difference in air quality. Everybody saw, what does that mean, air quality? Well, I'm not going to show that today, but there's lots of arguments these days about the fact that less aerosols, because of less burning, because of less transportation, led to increased shortwave absorption by the surface of the ocean, which led to less carbon uptake. Which meant that in the same moment as we locked down, the ocean refused to do its usual job. Just refused. Now, we could argue also about wildfires, but you might see that. That should show up here. And this is smoother. So I'm going to argue about other things later. But here's our atmospheric global temperature anomaly. It's nothing but scary. And here's the one I always like. Now this one stops because it was a 2013 IPCC report. And I think this one's prettier than the one in the 2021 report. But there's our atmospheric energy, right? This is the top of the atmospheric energy imbalance divided into the different places it's been absorbed. The atmosphere is that pink layer that you can't see. That's down at the bottom. And then there's a little land warming, a little ice melting, and then there's the ocean. It's the ocean. Now, why did the uncertainties narrow so far? It narrowed because we got Argo in 2004. That's why. Because used to be, we didn't do the ocean real time. We did decadal surveys once in a great while. You went out every 10 years, whether we liked it or not, did a long transect every 40 kilometers. You dropped the CTD over the side, all the way to the bottom, and made measurements all the way to the top. And the world's oceans are now extraordinarily everybody can argue about whether this year or last year was the warmest, but you really can't argue. It's always, always the hottest ocean. And that has a big impact. Transient climate response, the response in climate that you and me and our great grandchildren are going to feel is not equilibrium climate sensitivity. ECS that everybody talks about. I saw in Twitter, everybody's like, there's only 3 things about it. Our choices. Yes, you're right. Equilibrium climate sensitivity. No. Transient climate response. What is transient climate response? It's the ocean mix. I'm going to just say that. And what it means is that we warm at about half the rate. And by the way, these are not uniform. If you notice, just having a high equilibrium climate sensitivity does not mean you have a high transient climate response, because ocean mixing is not the same as high clouds. They aren't controlled by the same thing. They don't do the same thing. So in the same model, these are the same model, whether you're looking at transient climate response or equilibrium climate sensitivity, they're not the same thing. And yet what you and me and our great grandchildren are going to experience is transient climate response. It's the ocean mixing that matters. Okay, I'm going to get to the point here. There are all kinds of wonderful information that we need in the ocean that are also really relevant when we get out to the people scales. In Arizona, these are some of the things we're facing. California has some of the same things, but not all the same things. We did not get nearly the kind of snow that you guys did. We were praying to actually get walked a little harder with the rain. I'm only like 0.6 of an inch ahead of my water year. Let me tell you how sad this makes me. I really, we're in a 25-year drought. Our lake main water levels, the cities and the farmers are starting to line up with Colorado River water. Our drought is spectacular. Our heat waves make my summer with my kids indoors. Cabin fever for me is not good, especially for my drinking. No, just kidding. And I'll just point out that ocean funding has been going down, not up. I mean it. Look at that. That's through 2020. There is a percent of NSF total NSF OCE dollars as a percent of GDP. It's in the tank. I'm pissed. I feel like there are 6,000 oceanographers since AGU roughly working in the world today at PhD level. 6,000 of you, any of you who are thinking about oceans, bless you, bless you, bless you. We really need you. This is really scary. So here's the US, and I'm not even putting NOAA or NASA or the Office of Naval Research up. I could, but none of them had picked up the slack even a little bit. And here's another part. Let's talk carbon. Here's our carbon budget, right? That is those watts per meter squared we were just talking about. Everybody's like, let's cut food waste. I'm like looking at agriculture down there going, that might help. In fact, I think everything will help. So anything we can do, but really I'm looking at energy, right? All that orange and yellow. Electricity and heat, buildings, manufacturing, construction, transportation, it's energy, right? We got to stop burning. Now in the US, we're down almost 22%. This isn't updated to now, but we're down at least 20% since 2007. This is fantastic. Did you know we were down 20%? Hey, who here knew that we were down 20%? While growing our economy and our population at the same time. This is true decarbonization. Yeah, no joke. In fact, if we stay on the same trajectory by 2032, we will be at 50%, right? Yep, we went from 22% to 13% today of the total carbon emissions globally. And by 2032, we'll be at 6%. Hey, how about them apples? And we are also 22% of the global economy. So what am I trying to do with anthropogenic emissions? I'm going to look at, now Jim does a really interesting job on the land side, but I'm going to talk about the ocean side. We're trying to reduce the uncertainties in the ocean thing. Remember those decadal surveys and the fewer ships and the fewer ship days since 1989 at the end of the Cold War? Just by the way, over the pandemic, we dropped even more ship days. We retired more ships, didn't build more ships. Now, don't be depressed about this because us oldies are going to go get us more ships, at which point you guys can all come in and do great work. Woohoo! Not just ships either. So we have a problem. Our ocean sink from observational products and our ocean sink from models are further apart than they ever have been. Oh, this is scary, right? So we're trying to, and this is actually happens to be UN Decade of the Ocean. And everyone's talking about carbon dioxide removal. Thank goodness we have people like Patrick who are gonna help us make sure that we do it right and don't just, I don't know, spend a bunch of money that then doesn't get us anywhere. That would be bad. Thank you. Well, NOAA just rolled out a new program. In fact, and Patrick was on the top of my list for this. I'm chairing the session on ocean carbon dioxide removal in the Climate Intervention National Academy workshop we're having. So thanks for saying yes. And so here's what I'm worried about. We've got a biological cycle, and I was just talking to Keith about this, and we have the solubility cycle. And what I want to talk about is this. I want to talk about upwelling, because we can talk about what goes in, but I want to talk about what comes out and on what time scales. And of course, because I'm a Southern Ocean nut, this is how the world looks to me. Everybody's like, what is, all my students are like, what? Where are the continents? I'm like, well, they don't matter anyway, right? We're 72% of your surface. I don't need to worry about, stinking land. And here's my Southern Ocean, which looks complicated, but basically it's 85% of the global up of the ocean. I really mean that. I'm very serious. We are, it accounts for 67 to 98% of the excess heat that's transferred from the atmosphere into the ocean each year. And I'm looking at Remick et al. 2015. Accounts for up to half the annual oceanic uptake of carbon dioxide from the atmosphere. And something like could be as much as half of the biological production in the global ocean north of 30. The nutrients are supplied by the preformed that are not used in the surface layer of the Southern Ocean. So 50% of all the ocean carbon dioxide, 75% of all the heat. So when why do we rob banks? Because that's where the money is. Why does an oceanographer want to go to the Southern Ocean? Because that's where all the important things are going on. Not that it would be fun to go to Hawaii, but it doesn't upwell there. And we did such a good job with our communications that Henry Fountain wrote this fantastic article for the New York Times that made the front page above the fold last December. It was really exciting, and they used the data from CM2.6, which is GFDL's 10th degree coupled ocean atmosphere model, which we were using and had made public, GFDL approved public at the University of Arizona Cypress. So they downloaded it, gave it to an artist, and this is what they came with. I was like, what? So awesome. If I watch far enough, you'll actually get to the lovely ice shelves melting, which is terrible, but so I want to talk about this gas transfer velocity. So Wanacop has a new gas exchange versus wind speed relationship. He did the original, but he updated in 2019. Has everybody seen that paper? You probably haven't, but it's completely awesome. You know why? Because at the very high wind speeds, he made it more nonlinear, that you get more a faster bits of velocity with an increase in the wind, more asymptotic. Like, wait, really? And he's like, well, that's what the odds are telling us. And I said, but Rick, what if the winds were higher? He's like, well, that would give me the same answer. Oh, okay. So I think they are higher. And just by the way, high wind speeds are an outsized important to the carbon flux. This is just the wind speed distribution, and then I'm comparing that to the actual carbon flux distribution, which is of course offset towards the high winds. And this is why everybody tells David Ho and Rick Wanacop, why won't you do some more obs in the Southern Ocean? And they say, you go. And the reason is because it's really miserable out there. So, and oceanographers have to work very hard. They have to be away from, especially if you want to do an expedition in the Southern Ocean, you're going to be away for months. You might have 14 days of transit time each way. That's 28 days of just getting there and home. And the ship gets beat up and you get beat up and people get hurt and your electrodes break and you have to hang on to the wall and to your food and to your toilets, and you don't want to wash your hair because you have to close your eyes and it's shaking so much you might fall over. The whole thing is nuts. So here are all the measurements from ships from 1999 to 2015. Notice all the white space, especially in the Southern Hemisphere. And this is what it looks like today because of Argo. Because of robot floats. Oceanographers are sneaky and awesome. Now, the problem with this is it didn't start till 2004, right? Which is almost 20 years now, but still just a very, very short period of time if we want to talk about climate. And the biogeochemically censored floats didn't come along until the Southern Ocean Carbon and Climate Observations of Maui. I'm the moderator for that group. I wrote the original white paper, and it kind of grew with Jorge out of NOAA. We had the first ever climate process team from NOAA that did carbon, and it was specifically Southern Ocean carbon. That was the name of the CBT. And what we have are the usual Argo floats, except they have 6 sensors, not just temperature and salinity, but they also have nitrate, pH, oxygen, chlorophyll, and backscatter, which is the shizzle, I tell you. When it sits down at 1,000 meter, and every 10 days it drops to 2,000 meters and makes a profile up to the surface, and then beams that data back by Iridium satellite in a 5-minute burst, which goes through an automatic algorithm of quality control and is put online within 10 minutes, like that. It goes on to the global telecommunication service, so the entire world can see it, including all our weather forecasters, our ocean forecasters, our ecosystem people. It's free, right? The taxpayers paid for it, and we just make sure it goes right away. Now, I love this, right? Because there's one of my students, Becky Beethling, deploying floats. Her lucky cruise was out of Tahiti. I mean, really? That is not usually where I've been. So there she is putting one of our floats over the side. Fantastic. So 2 days of ship time is about 50K per day, bare boat. So it's 100K for 2 days. You'll get about 5 profiles. Now they're all the way to the bottom. These are hugely valuable, very important. But $100,000. Yeah, we could buy a float for less than 80,000 with all these lovely sensors on it, and instead of 5 profiles, you'll get 250. And this is what SOCOM has done so far through, well, okay, back to 2020, we've got even more out now, but they do die eventually between 3 and 5 years in. But it went from 0. So GoBGC got funded 3 years ago with the mid-scale research infrastructure. So they had to fight to the death with a bunch of people who wanted high performance computing and a new satellite and a really nifty, cool telescope. But they won, fantastic, because we've done this thing that said, what will we need to do to reduce the global carbon uncertainty to less than 1, from 1.7. And so we, Matt Maslov and I did this in the Southern Ocean State Estimate, which is a large chemically data assimilated model where we deployed floats, and these are the decorrelation length scales you're seeing, to calculate how many floats do we actually have to have. And it turns out, and this is just one of many simulations we did, we need about 800. So GoBGC got 500 funded, SOCOM had 200 funded, and that's 700. We were hoping that the rest of the world would match us. Now, we did get 125 more, so we were technically going to be over the threshold, but it came from 2 countries, France and Australia. And Australia, of course, is hitting way above their weight class. They have their own BGC Argo program. It's amazing. And part of it is they're sitting around on the doorstep. That's us with 9 of the 10 float deploying countries that we were hoping would help us because we need a big scarf. Not enough help as far as I'm concerned. And what we found was we're actually getting that degassing around the Southern Ocean, and we're concerned about it. So this is a lovely paper by Allison Gray, who's now faculty up at UW. And you can see these are actually genitals out now, oops. And you can see the lovely chimney of high carbon water from Pacific Deepwater coming all the way to the surface. That's for P16. Lynn Talley was actually chief scientist on that, and she actually made them back the ship up. She turned around and went back and said, I missed the chimney, we're getting it. And they did, they dropped the CTP right down the neck. This is also Veronica Tamsin's lovely Nature Communications paper showing it spiraling upwards over the topography, and our new papers that show the outgassing and the ingassing from the floats regionally and total. And this is what it looks like when you combine all that lovely data. This is oxygen data. Where it's brown is where you have undersaturated with respect to the atmosphere at the surface. Now, with the winds that high, how long do you think it would take to equilibrate? There's a little back of the envelope. How long do you think it would take to equilibrate if you didn't have massive catastrophic upwelling? Well, it would take like just a few days actually. But instead we have this spectacular upwelling and very low oxygen water. You can see it falling. There you go. So why am I worried? Growing winds. This is the trend in the top 10% of 10-meter wind speed, over 10-meter wind speeds from 1985 to 2018. and it's done from altimeter. And if you'll notice, there are almost no blue dots on this plot. The reason I like this is because you're basically looking at wave height, which is similar to what we get with scatterometer data, which is also looking at wave height, but from a different perspective. And this is the easterlies are ramping up. Triple diploid, anybody? We've just come through 25 years of almost consistently weak ensos and very strong La Niñas. The world is getting windier. This is from wave power, function of wave height and wave period. So this is Ruggiero et al. Increasing everywhere. And then we've got, of course, Hugh et al. Saying every major boundary current in the world is spinning up, except for the Labrador current. I'm just showing you the OBS papers, and then of course our gyres. This is Yang et al. GRL 2020. Gyres shifting polar increasing in strength. Now, how can the gyres be increasing in strength if we are warming like heck? Our whole ocean is warming, hottest ocean ever, right? And we're dumping fresh water in by the bucket in Greenland and Antarctica. The ramp up in our hydrologic cycle. Yeah. So we expected, this is a model result with some data on it. We expected the polar shift and intensification of the winds. We've been arguing about this for, I don't know, 15 years now. And we know why it would. We've got ozone cooling our stratosphere, right? Ozone loss cools our stratosphere. And then of course, even as the ozone hole is healing, we hope, we end up with greenhouse gases keeping the heat from getting to the stratosphere the other way or below. And the trend in the temperature anomaly for the northern hemisphere, the tropics, and the southern hemisphere is similar. They're all cooling. And when this is from the 2020 ozone hole, anybody, you could just tell me if you think that it's healing. You're not going to think it's healing, but hold on a second, just so you can visualize what I'm talking about when I say the winds are increasing. Here we go. And boom, there's our ozone hole. Yeah, I know. Is everybody scared? You should be. I hope you are. Okay, this is from the side. You're looking over the dome of Antarctica. Okay, and that was 2020, this is 2021. And it's so you'll see our jets to the left and the right. That's the same jet wrapping around and around, going in and out, and the ozone hole will dip, and there it is. There is what we call the polar vortex. It's a funnel. Did we see the funnel? Yeah, that's what it looks like. And just in case you thought the Arctic was going to get away with it, we had an Arctic ozone hole, 2020 and 2021, and this is the one for 2020. Anybody think that one's little? It's not little, it's big. Okay, so, and the ocean's tattling. I just want to say, it's not just the wave heights that's saying, oh crap, look at this. The Southern Ocean mixed layer are warmer and more stratified and much deeper. The dark blue is 15 meters or more deeper. And this is from JB Sally's fantastic 2021 paper. And notice, where is it getting shallower? If you look at the latitude from top to bottom, nowhere. Deepening mixed layers, not shallower mixed layers. And this is over 1970, that's 50 years, which we've been warming the entire way, right? The ocean was getting hotter the whole way. We assumed the stratification was increasing the whole way, and yet we still have deeper mixed layers. And this is why I think our reanalyses are screwed. I think they are all weaker. Now, these are the mean storm winds on the left, and we're comparing NSEP, ERA, JRA, and MIRA, all the four biggies for our reanalyses, right? And every single one of them entirely over the entire speed range is underestimated. Now, if you look at the max storms winds, it's even more underestimated. If you look at the total winds, all winds south of 40, you're looking at almost 30% under for all four products. So all of our modelers are going, look, we've got the winds right. I'm like, oh, except the winds that you're comparing to are wrong. Now, why? It turns out that the US had a scatterometer, that's whatever, QuickScat. In fact, that data, that crossover data comparison is from QuickScat. And we have almost 8 of these up right now, but because 3 different countries put them up, we ended up with them all in the same hour. So we get 2 measurements per day of these massive cyclones in the Southern Ocean and everywhere else, 2 measurements per day each. Do you think you can look at the winds really carefully in a hurricane with 2 measurements per day for 24 hours? No, you really can't. And so just scatterometers use lovely radar beam, bounce it off the waves. The more that's diffused, the higher the wave must be, right? It's really, really stupid, you know, and we've got better tech now. It's pretty awesome. There were a bunch of different ones. Most of them have failed. We still have ASCAT. We still have high 2A and OSCAT. Now, one of the problems are that a lot of our other means of looking at winds have repeat timescales, not just of twice per day, but like TOPEX was 10 days for an exact repeat. Jason was 10 days, we had 36 days, you know, it depends on the satellite when they'll repeat back to the same location. So basically you need an ensemble, you need an array, a constellation. You can't do it with just one, it doesn't work. Partly because, so here's just why do we think they're undersampled? And I'll just show you what happens. So we proposed with a bunch of friends, especially my friend David Long, who built QuickStat, and he was the instrument lead at Ball Aerospace. We proposed actually a mission to actually get the winds we need. And it got shot down. But it was a lot of fun because I got a commitment from NOAA to actually let me borrow one of their P3 hurricane hunters and take it to New Zealand. I know, I got a letter of commitment. I'm like, and nobody's appreciating how important this is. Somebody in the review team was like, they'll never let her take it. Look at the letter from the director. I can totally read it. And this is why we're worried about it. If we added one more scatterometer orthogonally orbiting, basically orbiting 6 hours apart. So we get 2 per day to 4 per day with just one more satellite. That's it. Because all the satellites right now were phase locked together because they were all worried that they were going to get the wrong answer. So they made them all go together. Each country did the same thing. They launched them on the same orbit exactly the same time because they wanted to make sure which means we only get 2 per day with 4 satellites up. It's terrible. So this is what we were going to get. So we would go. So notice if you undersample, everybody who's ever done paleo understands this utterly. If you don't take enough samples within your core, you are going to miss really important things. Your peaks, your lows, the in-between. So what we did was we took the Southern Ocean State Estimate, which is a MIT GCM with 40 bar data assimilation of our lovely floats. And we added a whole bunch of seals and other fantastic data, which really helped us out. And we ran the model with what ERA said the winds should be. And then we ran it with ERA plus 20% in the momentum, which is basically like Delwith and Zang or one of the other FAFMED, which is one of the CMIP intercomparisons. And when we add 20% winds, we go from nearly zero outgassing to flipping the sign for the Southern Ocean. It's just F equals MA. We add more force. The time equals mass times acceleration. We move more mass. So the surface is full of carbon and it wants to degas. And it turns out, so we checked, if you do with so the top ones are with the winds with no adjustment, and the bottom one is winds plus the adjustment. And what it turns out is we get only 81% of the carbon with ERA normal. And if we add one more satellite, we get 96%. Now, if we increase the winds, we only get 71%, because remember, those high wind speeds have a disproportionate impact on the total carbon flux, right? High winds. Remember, I showed you that a little bit. So if we increase the winds by 20%, we miss even more. We're only 71% of the total carbon can we reproduce by with only one set of satellites. If we add one more, we get up to 96%, even with the increase in winds, which is what we would need to do. And we've turned that into some really cool prediction. This is was my student now off making. He went to work for the Navy and got offered a job at a major bank doing climate analysis. And he makes twice what I do. And he said, I feel really bad with this. I don't. Come back to our alumni reunions. So So I want to show a little bit about what this means in our system model framework, because everybody's like, well, they're system models, right? Some of them must be high winds and some must be low winds. We must be enveloping the possibilities. And all of my senior colleagues here are shaking their heads because they know exactly. No, the winds are always too weak. They were too weak when we had the reanalysis we had. Now that we know the reanalyses are wrong, we're in real trouble. This is bad. So I just want to point out that we only got to stratospheres, upper atmosphere, that blue line up there recently, very recently. And most of our coupled climate models, Earth system models, don't have what we call a high top stratosphere. Lots of layers up through the tropopods and into the stratosphere where it's cooling. Remember, I just showed you those on all of that. And they didn't have all the stratosphere chemistry and all the rest of it. At this point, our best models are down in the observational error. I love this. It's a climate Turing test. Can anybody tell me which one is the Earth? There's just one on there that's the real Earth. Everything else is climate models. Yes, my lovely pattern recognizers, you probably get it right, but and I borrowed the Suki. Suki has been helping me with our modeling at the University of Arizona, and Ron Stauffer now works at the University of Arizona, not full time. He's technically retired for GFDL, but I got super lucky that he agreed to come work for me. I mean, he got Suki a Nobel. I mean, who knows what we could do? But the University of Arizona is now the first university in the world to actually run the deck for the IPCC. We are one of the official models. It's called UA Manabi model. Now, I will admit that we are only in the middle, maybe a third at best. We are not like CSM or GFDL's state of the art, because that would be way too expensive. But we did do some analysis to see what would happen. Now, those are the winds you'll see to the right from CMIP 6 and the Antarctic sea ice extent. And you'll notice that our Antarctic circumpolar current, which is on the far left, is weak in almost every model. There might be 5 or 6 that are correctly. So there's been improvements, but there's still some very serious biases. Let me see, this is supposed to be. And if we compare, remember we're looking at that transient climate response. If we compare how much uptake by the ocean of cumulative carbon uptake under the highest scenario, the spread is equivalent to 100 petagrams of carbon net atmospheric change, about 52 ppm. Just the difference in the ocean carbon uptake. Yeah, that means, so when the IPCC folk came out, they said 3 things matter: our choices, equilibrium, climate sensitivity, I still think that's wrong, and carbon feedbacks. I'm like, hey, this is the big one. And yet we have one figure in the entire report, one, that says this, one. And it's not that figure is better than the one they have in there. Sorry, Becky does very nice work. So here are our ensemble means. We looked at this, both our surface air temp, our SST. When we have a higher mixing ocean, we end up with, we don't warm as fast in the atmosphere. Makes sense, right? The ocean takes up more heat, the atmosphere is left with less. And it actually doesn't have to be that big a change in the mixing. We did this too, where we added the melt, because, you know, none of our scenarios actually include freshwater forcing from Antarctica melting or Greenland. I know. For all the cryosphere people, you must just be beating your heads against the wall, because how do you get the IPCC to actually consider the dynamic impact of extra freshwater? So we did the winds, we did the freshwater, and then we did one with both. And this is in FACMIP, it's actually the flux anomaly force MIP. It was we got it accepted as a set of scenarios. And my postdoc got these fantastic papers. So there's, oh, well, this is Becky, but we also have one. So those are that's what they're called. In fact, with this FAF water stress, etc. And then Ben wrote these 2 great, my postdoc, who is at his, okay, so first he went to be the VP climate analyst, because he said his girlfriend, okay, I shouldn't say this out loud, really wanted this fancy apartment in London. Hey, happy life, very important. And now he's at his startup with his friends doing climate analysis. And so change in future, what we did was we added freshwater to just the freshwater. This is the freshwater result. What we found was the normal function of the ocean around Antarctica is to bring water up that releases heat to the atmosphere. That's normal for the ocean. You move heat from the equator to the pole and then you release it, right? You make it colder. Now, in fact, we are taking up some anthropogenic heat now, but in general, the ocean is supposed to move heat from the equator to the pole and release it, right? Keeping us relatively evenly distributed. Now, when we added extra freshwater, it had a whole bunch. We did this in ensembles, so nobody could say, we're just getting a one-off or an anomaly. It cooled the globe in the air temperature, right? We warmed more slowly. That's a better way to say it. It didn't cool. It warmed more slowly because of the freshwater, because it inhibited some of that release of heat from the ocean to the atmosphere. The normal function of the ocean was inhibited by the extra freshwater. Makes sense, right? But that meant that we warmed more slowly. That transient climate response. Remember, we're talking about that. Here we are. It also shifted the ITCZ, changed who was drying and how much. Just by the way, these are going in the direction that we are currently seeing today. And it changed the sea ice area. When you freshen the surface layer, it freezes more quickly because it freezes at a higher temperature. Freshwater freezes above the temperature, that you would freeze saltwater. So more freshwater in the surface layer ran the sea ice out further, which is what we see, what we expected. And the sea ice area matched really nicely over all this. But what we're really worried about is that if we assume that there's a feedback, basically the upwelled water increased the temperature, the warming anomaly increased by more than 4 times. So what we were pushing up against Antarctica and melting ice along the edges there. Remember, everybody knows the Western Arctic Peninsula is below sea level, right? There'd be 2 or 3 little islands that'll stick up once that ice sheet's gone, because everything else will be underwater, which means that changes at 400 meters are changes to the ice edge. It's not land, it's ice. And it was a lot. So if we melted more, we would see a 10 to 40% increase in the freshwater input from ocean melt, just associated with this freshwater induced anomaly, which we thought was big. So we then pushed it to, okay, we take the freshwater, that was one paper, and then this one came out in Nature Geo, and we took the freshwater, and that's the left hand, it's just the freshwater, and then on the right, we have the winds, and then the bottom, we did a third set of fronts, which is winds plus the meltwater. And that dipole effect that we see in the bottom, which you don't really see in any of the others, is exactly what we observed from the flows, which was pretty exciting. So there's our combined, etc. And that had a big impact on both the oxygen, which actually increased, because with the increased winds drives an increase in oxygenation, which we observed from the flows. It also decreased the nitrate north and away because at the surface, because it was deeper, exported deeper. So we're just at the beginning of seeing where we can go with this brand new real-time carbon, nitrate, pH, interesting set of data. And I'm hoping we will eventually get that other satellite we need, but we didn't have any of these things even 15 years ago. Supreme Court ruling that the Clean Air Act includes carbon as pollutant, that's 2007. The Paris Agreement, a political agreement to address carbon cycle, carbon observing satellites like OCO2, or system models that included the full carbon cycle. We didn't do that in 2007. And then these carbon sensitive flows like SOCOM and WGC, we have all the pieces to be doing more closer to real-time carbon analysis, and we're doing it on the part of the system that is least explored and most likely to bite us in the butt. I mean, have unintended consequences. So thank you so much. I would love questions.
How do we know that the scatterometer is not the one that's wrong, given that the reanalysis is constrained with all these other data sets? Like when you plotted ones against the other, there was a clear bias. Why do you know that it's the reanalysis that's wrong and the scatterometer results are the treaty?
Well, in the Southern Ocean in particular, it's only sea level pressure. There isn't anything else.
There's no data there.
No.
Okay.
So there is
Nobody ever trusted the reanalysis in the Southern Ocean.
no. I mean, No, actually, I'm trying to think, like, mostly, and the big problem, with, we already, everybody who worked with NSEP and at ERA knows that, that sea level pressure, has two, in the west at least, has two main modes of action, one at the surface, near surface, and one at the tropopause height. And they usually in the southern hemisphere go together, but they can split a little bit apart. And but sea level pressure looking up basically only sees the combined. And NSEP put it all in the, this is why NSEP was so much higher winds, because they put the sea level pressure anomalies in the lower part of the center of action, and ERA put it in the upper. But without any physical evidence like, you know, sea surface, you know, altimeters or scatterometers, we had no evidence for one or the other. Now we have a lot more evidence that this is, and of course the mixed layer depths, and I mean, there's many things that are now telling us the ocean's not lying to us. There's no way to make higher wave heights, deeper mixed layers without wind. Literally no way, especially the wave heights. There's just no way to do that. And we're literally fighting between warming and freshening, stratification, impetus, and winds. They're head to head.
That's the follow-up
Yeah.
question. Is there any effort to redo the reanalysis, including some of the scatterometer data or some of the?
They include the scatterometer data. Our scatterometer data moved out 7 years ago, and we haven't replaced it. And the new designs, which would be awesome, are not being, we're not implementing. I think we're in trouble. I am really worried that we actually are looking at, when I look at the ozone and the cold temperatures, you know, the ozone hole this year closed in January 6th. Last year it closed January 21st. They should be closing end of October or early November, and they're lasting. And those are, when we say ozone hole, I mean temperature. That is a much colder temperature as long as there is this ozone loss. And it's affecting our weather, it's affecting our ocean, the stirring of our ocean. Yes, it might mean that we take up a lot more CO2 because the solubility will be exposing cold water to the atmosphere. And if that's great, as long as the cold water is the Pacific deep water, at which point we are in, you know, everybody laughs because the land wildfires are such an obvious visual representation of carbon back into the atmosphere, but the total on land is less than 600 petagrams, right? And in the ocean, all dissolved is 24,000 petagrams of carbon, and it's just there to be exposed to the atmosphere the second it upwells. Now, and everybody's assuming that the ocean is slow, and I'm just thinking that maybe we're assuming it's slow because we only used to visit it every decade, and then now that we've got Argo and BGC Argo, that should change. I'm worried that in fact that COVID response, that one-to-one response within a 2-month lag might be real. In fact, I have a paper with some people that we're submitting right now on this. It's terrible.
Could you just make sure to repeat the question?
Sure, I will, absolutely.
But I think.
But that's an excellent question. But I have thought very carefully about these things, that specific problem. Yeah.
Could you please explain again like the positive feedback with the heat in the fresh water? So I'm trying to understand, is it because the fresh water is warmer than flowing water or?
Normal, especially normal deep water is 3 to 6 degrees Celsius, and most of the Southern Ocean produced water is 0 or colder. And so if you upwell, if you put fresh water in, you tend to weaken the exchange at the surface. You literally have less water making it all the way to the surface and exchanging with the atmosphere. It's like putting a lid on it. But it doesn't say none, it just slows it. But slowing it actually means the normal function of the ocean, the thing that would happen in pre-industrial whatever, is to move heat, especially Northland deep water, to the pole, upwell it to the surface, and release that heat. If you put the lid on, you basically weaken that, and the subsurface warms like 4 degrees or more, actually right up against the feet of the glaciers, which then would melt more. Now, we didn't do a fully interactive visit of it, allowing it to melt more like with a sponge layer or something awesome. We didn't do that. we just calculated how much more could melt if we warmed it by 4 degrees. But the 4 degrees was just a function of putting, and by the way, it scales linearly. And we tried doing it like in little tiny dots, like just the weights and just other things, but it scales. It turns out it swooshes along it mixes very quickly at the surface, the fresh water. It stays relatively in the surface, doesn't mix down very quickly. And it's the effect of the lid is stronger with more and weaker with less, but it doesn't seem to care where we put it. So we did sensitivity studies all the way through to enormous to not very much, and the effect is always the same, it's just more or less.
What is the role of decadal variability in southern?
These days, not much, it's all trend. I'm not even joking, I wish I were joking. I think 20 years ago, when I was working with Mike Wallace, we were arguing about whether or not the southern intermode impact would continue or whether it would recover with the ozone. But the trends in the cooling, since we now hit both polar stratosphere cloud and levels in a cold ozone holes, we hit not just the water creating ice, but N2O too. So we're actually I think we're in for it. I don't think those ozone holes are going to recover. I think the increased greenhouse gases are going to continue to push us that direction. I think the winds are at best going to stay the same and at worst could get much worse. And by the way, did you notice that it wasn't just the westerlies that were increasing? The wave heights say the easterlies increased too. And by the way, I think we're in a La Nina state. So all the people who bet on El Nino, wrong. And the models, half the models said more El Nino like, and instead what we've got is a transient. Everybody knows the QBO blew out twice in a row, right? Right above the quasi-biennial oscillation, which is right above the tropopause and tropics, got blown out not just once, but then again. And I think we have been in IPCC land. We've been thinking a lot about equilibrium condensivity and not at all about the transient. I think we ignore the winds because on land, the winds don't matter. Precipitation matters. Because stirring doesn't do squat to the carbon cycle on land. I mean, maybe you get more inclusive or wildfire conditions or evaporative stress or something, but really not that much. In the ocean, winds are everything, right? The stirring, how deep, how wide, where, how much, who gets to eat what. It's all about the winds, right? And there are 6,000 oceanographers, half of them are marine biologists, and we're just a tiny voice, so small. We just get swamped by everything else, and we're willing to let our scatterometers die and not replace our icebreakers. And I'm appalled. So yes, I'm a little noisy because I am deeply concerned that we aren't arming up our oceanographers with the tools, equipment, and hands. You know, we need peopleware, you know, humanware that will be able to tackle this challenge. 72% of the Earth's surface, 98% of the 93% of the heat budget, 1 out of every 4 car molecules out of anybody's tailpipe anywhere in the world, and it's the responsibility of 6,000 humans out of 8 billion. I cannot tell you how much this makes me nuts. So everybody should do oceans. Come on in, the water's fine. Any other questions? Just by the way, young ones, you're needed. You know, the next time you're having a bad mental health day, let me just tell you how much you are needed. I'm just looking at all these faces going, reinforcements. It's what we need. It's desperate. I don't care what industry you go into, where you take your amazing brains, but we need you. You are needed. Please continue. Let us help you.
Amen.
Thank you.